Okay, so we're on page 6 talking about circular motion. Newton's first law of motion, which is the law of inertia, says that an object will remain in motion in a straight line unless a net force acts on it. Will remain in motion in a straight line unless a net force acts on it. This means that there must be a net force acting on an object that's moving in uniform circular motion. There has to be a force, a net force, otherwise it would be traveling in a straight line, not a circle. So some examples of circular motion, if we have a rubber stopper on a string. So this is basically an object tied to a string, and you can get it moving and swinging in a circle, and this object will continue to travel in a circle. What is the source of this force that causes the rubber piece to travel in a circle rather than a straight line? The source in this case, the source of this net force, is the string. The string is providing the force that prevents this rubber object from traveling in a straight line. And we have the Earth going around the sun. Maybe this one's the easiest to see. The Earth is traveling in an orbit around the sun. It's mostly a circle. What is the force that holds the Earth traveling in this circle rather than just traveling in a straight line into space? And the source is the sun's gravity. What about the mass on the turntable? Remember, we have this wooden disc on a turntable, and it's just rotating in a circle. And this mass is just an object that sits on top of this circle and travels around. Maybe a little bit easier to think about is a car that is going around a curve. What is it that keeps the car in contact with the curve? What is it that makes the car travel in this circular pattern rather than just driving in a straight line into the field? In both of these cases, the source of this force is friction. The friction between the tires and the road hold the car onto this curve. What happens if the string breaks? If the string breaks, the stopper is going to travel in a straight line, and that straight line will be tangent to the circle. And your math, physics version symbol for a circle is this. What happens if the sun's gravity suddenly disappeared? The inward force is no longer there. Earth would travel into space in a straight line. That straight line would be tangent to the circle. If the friction isn't great enough for the mass on the turntable or the car rounding a turn, what happens? The mass slides off. Travels in a straight line. In these instances, when the string breaks or the gravity's gone or the friction isn't great enough, the inertia is greater than the force trying to hold it in. The force that causes object to travel in a circle instead of in a straight line is directed inward towards the center of the circle. There's a word that means acting toward the center. Centripetal. Centripetal means acting towards the center. In order for an object to travel in a circle, there must be a centripetal force acting on it. The symbol for centripetal force, Fc. Now there is another word that's commonly confused, centrifugal, and that's not a thing. Centripetal. Newton's second law says that if a net force acts on an object, it will accelerate in the direction of that force. How can an object that is in uniform motion be accelerating? Here's a true statement. An object in uniform circular motion is continually accelerating. To see how this is possible, look at the original definition of acceleration, the rate of change of velocity. Some notes here. Velocity is a vector. It includes two things: magnitude, which in this case is speed, and direction. Since velocity is a vector, it has both magnitude and direction. All of the accelerations we've talked about so far have been a change in the magnitude of the velocity, from 30 miles per hour to 50 miles per hour. But this acceleration is due to a change in direction. Our new acceleration is due to a change in direction instead of a change in speed. Since the acceleration must be in the same direction as the net force, this acceleration is directed inward and is called centripetal acceleration. AC. Now, the fact that this acceleration is directed inward might not make sense at the moment. We'll get there. Regular acceleration is a measure of how quickly the speed changes. Centripetal acceleration is a measure of how quickly the direction changes. Some formulas for these vector quantities. Velocity. We've already seen this one. 2 times pi times the radius divided by the period. This is how far it traveled. This is how long it took. Distance divided by time. Or it could be in terms of frequency. 2 times pi times the radius times the frequency. The formula for this vector quantity of centripetal acceleration, the velocity squared divided by the radius. the centripetal force uses Newton's second law, the mass times the centripetal acceleration. Some pictures for the direction. So let's imagine we have this rubber stopper tied to a string and I'm swinging it in a circle. So here's the center of the circle, here's the string, and here's this rubber stopper. I am spinning the string in this direction, which means that it's traveling in a circle like this, and the rubber stopper is, velocity is in this direction. Now the speed is going to be the same, but the velocity is always changing because the direction is always changing. The velocity is tangent to the circle. So what is the direction of the force here? So here is the same diagram. Here's the rubber stopper. There it is traveling in the same circle. Try that one time again. Good enough. Whatever. So imagine that this is a circle, not whatever this is, and it's spinning in this direction. What is the direction of the centripetal force? Remember, centripetal means directed towards the center. And so this is an inward force, which means that the force in this diagram is oriented towards the center. This is the centripetal force vector. It is oriented towards the center.